Okay, welcome. So today we'll be looking at quantum states, bras, and Kets. And this is taken from chapter 2 of Vlatko textbook, Introduction to Quantum Information Science. So let's begin. A quantum state can be written in the following way. Ket psi is equal to alpha 0 plus beta 1. So this here is a vector, and we call it Ket notation. And it's for pure states. Later on we'll look at a more general case where we can represent non-pure states or mixed states in a density operator formalism. But for the moment here we have a simple example of a quantum state where alpha and beta are complex numbers. So alpha and beta are in the complex domain. Now, what we can say here is we can look at 0 and 1, and these form the basis states, or the basis vectors of our ket psi. So in matrix form, we can write ket 0 is equal to 1, 0, and ket 1 is equal to 0, 1. So they form the bases of our overall ket psi. Okay, now let's call this equation 1 here. Let's write equation 1 in terms of the matrix form. So what we can look at first is looking at this here, we have alpha times ket 0. So let's do alpha times ket 0 is equal to alpha 0, where this has simply come from multiplying alpha to this here. And we do the same again for ket 1. So we do beta times ket 1 is equal to 0 beta. Okay? Now coming back to equation 1, we simply add these two components to get what ket psi is. So ket psi is equal to alpha 0 plus 0 beta is equal to alpha beta. Okay? So we have ket psi is equal to the column vector alpha beta. Now let's look at another type of vector, and that's known as a bra. So let's just scroll down for a second. Okay. So a bra is the complex conjugate transpose of a ket. And we can write it like this. Bra psi. Now we just said that it's a complex conjugate, so let's refresh everyone's memory of what that is. So we have a complex number, x plus iy. Okay. Now if we want to find the complex conjugate of this complex number, we write it like this. So x plus iy with the star up here, that means complex conjugate, is equal to, now all we simply do is wherever we see imaginary component, we put a minus that. So in this case, it's x minus iy. So that is the complex conjugate of this complex number here. Okay, now we also said it's a transpose. So the transpose of a matrix, let's say we take a matrix 2 by 2, A, B, C, D. Transpose of this, which is written as this matrix transpose T up here with still A, B, C, D given here. Now that's equal to, simply put, we take all rows, they become columns, and the columns become rows. So here, this row here becomes a column, so we put it down A, B here. Now this row here also becomes a column, so we put C, D here. So this bra is the complex conjugate transpose of bra, of our ket psi. Okay? So what that means is we had before psi is equal to the column vector alpha beta. So that means we have beta is equal to, oops, let's get rid of that. So actually let's just Remove that there, erase that. What we wanted to write was, okay, so coming back here, now bra of psi is equal to, now we take the complex conjugate, so what we'll have is alpha star and beta star, and all the rows, so this column now becomes a row, which is a transpose. So we have a row here with alpha star and beta star. So this is the bra now. Bra. And we have over here what we introduced originally, ket. And these are just, think of these as vectors, but a special type of vector that we'll be dealing a lot with in quantum information. Now, let's scroll down a little bit further again. So let's put that down there. Now coming back, we can then write bra in the Dirac notation. Bra psi is equal to 0 alpha star plus 1 beta star. Now remember here, we had the complex coefficients at the front. They all become now the complex conjugate of themselves. So this is this here. And wherever we had the kets, they now become bras. So now we kind of flip it to the other side for the 0 and bra 1. Now a common and useful mathematical operation in quantum information is what's known as the inner product. Inner product. We're going to see this a lot, this type of operation. And mathematically, it looks like this. The inner product between two vectors, phi and psi, can be written like this. So you can see it's made up of a ket psi, and to the left of it, we have bra phi. Okay, so now let's move on, and let's actually look at an example now. So let's calculate. So let's write example here. Example. Okay. Example, calculate the inner product of psi with itself. Now remember, just so we don't forget, psi, we've defined it previously as alpha 0 plus beta 1. Okay. Okay, so if we want to calculate this, we need to find the ket. Well, we have it defined there, but we also need to define the bra. The bra is just defined up here. Okay, we just defined that. So we're looking at the inner product. Now, essentially what we want to do is multiply this bra by this ket. So let's now do that and see what we get. So taking the bra at the top, let's just look at it, put a bracket around it so we know what we're looking at. Plus 1 beta star. Now let's put in the ket psi here, which we've talked about, plus beta 1, like this. Okay, now the next step is simply to think of it as multiplying through everything. So we've got this term here, we want to multiply it by that, and we take the same term again, multiply it by this, take this, multiply it by that, and this, finally this multiplied by that. Okay, so let's do that. Now, let's take the first example, this multiplied by this. The coefficients out the front are unaffected by the multiplication of the kets and bras. So what that means is we can grab them, take them out, and let them be by themselves. So we have alpha modulus squared 0, 0. Now, what I've done here is alpha star times alpha is just simply equal to the modulus of alpha squared. Okay? And we have bra 0 acting on ket 0. We'll come back to that in a moment. But let's finish multiplying everything through. So we have alpha star, beta, 0, 1, okay, plus, where are we up to now? We've got beta star, alpha, 1, 0, plus the last term now, we're going to have a modulus squared again, but this time of beta, and we have 1, 1. Now this is where things become interesting. What happens now is that we assume quite rightly that it's a basis, ket 0 and ket 1 are formed for our state. And it's normalized. So what that means is that these are orthogonal. All the basis elements are orthogonal to each other. So whenever we see things that are not the same here, we get rid of them. So this goes, and whenever things are identical, so we have 0, 0 and 1, 1, when those both elements are the same, it's normalized to 1. So we assume that's normalized to 1. Okay? So putting everything together, what we find is the inner product of psi with itself is equal to alpha squared plus beta squared. Okay? So the modulus of that squared. So some of the things to take away from this finally is that we use the orthonormal conditions. So just reiterating again, anything that's the same, we assume it's equal to 1 here, and anything different, it's equal to 0. So they vanish from our calculations. So in the end, the inner product of psi with itself, where psi is defined in this way, is equal to the modulus squared of alpha plus beta squared.